Hello everyone, this is Azir, and they were going to solve some tasks from Great Forces. This is not Samuel, it's one task, and this is 1800 rated task, and mainly today I will try to solve it. This is type of graph, and this is one of algorithms in graphs. I don't know about graphs anything, like I know that they're weighted, unweighted, and others and others. I have only know DSO and how to implement graphs. So let's get started by learning some algorithms. I think so it's one algorithm for this task, and I hope I'm going to solve this for a day because it will be an incredible event for my life. So let's get started. I think that's pretty good. Yep, so this is type of shortest path. Yep. There are 47 accepted submissions for this task. Well, it's Dijkstra algorithm. Well, I really don't know how to read this. Okay, so wait a minute. Yeah, it looks as a graph. What contest is this? Call the forces alpha round. This is C task. What about B task? B task. What the hell? What mass is this? How do I know this is 1200 rated task? Yep. Holy crap. What is this contest? Like hell nah. How it's even possible? Like. Okay. You are given a weighted undirected graph. The vertices are animated from 1 to n. Your task is to find the shortest path between the vertex 1 and the vertex n. You are given a weighted undirected graph. The vertices are animated from 1 to n. Your task is to find the shortest path. The first one contains two integers n and m, where n is the number of vertices and m is the number of edges. Oh, okay. Following m lines contain one edge, each in form a y b y and its weight, where a y b y are edge endpoints. And oh yeah, I see. It's possible that the graph has loops and multiple edges between pair of vertices. Okay, right. Write the only integer -1 in case of no pass. Oh, it's possible. Okay, so oh, I'm sorry. So let me take this graph. So what do we get? Yeah, now it's good. From vertex 1 to the vertex n. It's given right there from 1 to 5. Is it? Oh, holy crap! It looks really interesting. Let me edit this graph. Let's put it right there, like this, like this. It's circled and it's weighted and it's undirected. That's all that I know. Now it's pretty good. Okay, as we look to our graph, let's take a shot. Well, let me just take some time right there for writing it. Mainly, so we get graph 5, 2 and 1. This weights 5 and 2. Then we get 1 right. Oh, it's 3, 1. Then we connected with 2. It's weight of 4. Then we connected with 4. Here and here. 1 and 3. Yeah, now it looks pretty incredible. From 1 to 5, the shortest path, mainly we need to print its weight. Write the shortest path in opposite case. If there are many solutions, print any of them. This is constructive. Like we need to go by its weight. How would I say? Like I don't know. Or we need to print what? In opposite case, like if there are verses, or is it weight? Are there weight? Let me check it out. Like there, as we could see, let me make it black. So yeah, as we could see, from 1 to 5, there are, it's 7 weighted, and mainly it's 2 and 5. Then the second one is about, so what if from 1 3 1, like I mean 4 and 5, there is going to be the sum of weights. The sum of weights is going to be 4 5 5, and then 1 3 1. Oh crap, I missed. Nope. Let me check it out. Like type of is going to be its weight is 5, and mainly it's 1435. 1435. That's all that I could say. Yeah, that's what I say. But what about, no, I go like this, like this one. I couldn't exit this. Yeah, how would I say this is the smallest one? Yeah, so also the graph was beautiful. I'm glad for this. Okay, let's delete and to go for secondary. Holy crap, wait a minute. Pretty normal. Let me edit. 4 1. From 1 to the end again, and is the same graph. No, like there's no 6. Really. What the hell is going on? There is no 6, but there's something is not right. Holy crap, yeah, I see you, man. Okay. Okay. Yeah, this is the same array, oh, I missed. This is same graph. Oh, it looks beautiful. I'm glad for this. Five to 1, and 3 is there. Yeah, it's the same. Yo, are you joking, man? Like 1 2 2 2. This is the same. Okay, it's enough. Mainly, I have heard about shortest passes, and also I have heard about Dijkstra algorithm. I will try to solve it, but firstly, I need to know how to work with shortest pass. Um, let's get started. Like, I mean, it the introduction was going for 9 minutes. Okay, let's start with something new. Okay, I see it all. Then about I need some books right there. I mean, like hell, where's my books? So I'm gonna need to block my screen for a while. The main problem is that I couldn't find them, so I'll go by like searching them. One of them was Competitive Programmer's Handbook. Also one of them was Pops Yusako. Like, is it going to give me Principle of Algorithm Problem Solving? Yeah, let's go. This is Computer Programmer's Handbook, Graph Algorithms, Advanced Topics. String cause person, yep. What the hell? Didn't find it. What was that? Oh, let's go. That's the one. Okay, but what about that one? Like, I couldn't find. Oh, yep, here it is. Yeah, yeah, that's the one. Also, I like to open its script that's possible. Is going to be in CP algorithms. Um, so okay, let's get started by starting it. Weighted shortest path, Dijkstra algorithm. Like, I mean, it starts almost here and it's there. It's all. What about like? Okay, so what about here? Oh yeah, there are lots of to study. Holy crap. Okay. And what about here? Yeah. Yeah, it's pretty good. Dijkstra. I don't know what's Dijkstra even like. I think so it's possible that we also could make it without Dijkstra. Like, what about Wikipedia? Um, okay. Okay, let's read mainly. Uh, Dijkstra's algorithm can be seen as an extension of the breadth first search that works for weighted graphs as well. Single source shortest path non-negative weights. Single source shortest path non-negative weights. Given a weighted graph, okay, where all weights are non-negative, okay, a source vertex is compute the shortest distance as a for all. It has a similar. What about? Wait. Nope. I was thinking about boot first, but okay. Uh, However, can be this case for every vertex adjacent to S. In particular, can be neighbor to S with the smallest edge weighted W to S have a distance smaller than W. This is never the case in figure to do and actually holds in general. Assumes that this is not the case in figure to do. In figure to do this hypothetical scenario is shown. Any such path must still pass through some neighbor W of S. By assumption, the weight of the edge SU must be larger than W, which I don't know. This reasoning at least allows us to find the shortest path. I couldn't understand anything, like, man. Additionally finds the shortest path from the starting node to all nodes of the graph, like the Bellman-Ford algorithm. You're joking, man. The benefit of Dijkstra's algorithm is that it's more efficient and can be used for processing large graphs. However, the algorithm requires that there are no negative weight edges. Wait a minute. Oh, I'm lucky. Okay. Yep. Then where's this? Okay. Like the Bellman-Ford algorithm, Dijkstra's algorithm maintains a distance to the nodes and reduces them during the search. Dijkstra's algorithm is efficient because it only processes each edge in the graph once, using the fact that there are no negative edges. Okay, what about Bellman-Ford's algorithm? Functions pass from a starting node to all nodes from the other algorithm can be processed all kinds of graphs provided that the graph doesn't contain a cycle with negative length. If the graph contains a negative cycle, the algorithm can detect this. The algorithm keeps track of distance from the starting node to all nodes of the graphs. Initially, the distance the starting node is 0 and the distance to all their nodes in infinity. The algorithm reduces the distance by finding edges that shorten the passes until it's not possible to reduce any distance. Example, let us consider how the Bellman-Ford algorithm works in the following graph. 1, 2, there's also 3 5. It's 0 and there are infinities. And okay, each node of the graph is assigned a distance. Initially, the distance to the starting node is 0, and distance to all other nodes is infinity. Okay. First of all, edges from node 1 to this distance. Mainly, firstly, it's found there, there, and there. After this edge, after this, it's 2, 5. Like it goes to 2, 5, and 3, 4. It's just from there. Okay, 2. And there's going to be 1. Finally, there's one more change from 4 to 5. After this, no edge can reduce any distance. This means that the distance are final and we have successfully calculated the shortest path. This is from starting node to all nodes of the graphs. Like it really looks like as an dynamic programming or even knapsack, if I don't miss. After this, no edge can reduce any distance. This means that the distance are final and we have successfully calculated. Okay, for example, the shortest distance 3 from 1 to node 5 correspond to this. Okay, man. Okay, so wait a minute. 3 plus 1 is 4, 4 plus 2 is 6. Okay, I see that. Okay, like this type of pairs, like they're For example, at graph from 1 to 1 is 0, from 1 to 3 is 3, from 1 to 5, from 1 to 2 is, oh crap, I missed, wait a minute. Like for example, from 1 to 1 is 0, from 1 to 3 it's 3, from 1 to 2 is 5, and so on. Okay, I see, man. And here's how it looks like. Implementation, like this. Okay, that's pretty interesting. Okay, distance x 0. What is, wait, for year outer edge. What of implementation is this, like? What is tie? Or it's built in. Mm-hmm. Yeah, I see. Like this is type of making tuple. Okay. Yeah, I see, man. Okay. Negative cycles. Yo, crap. But wait a minute, I couldn't understand. Like, I save H at. Oh, I don't know. Okay, negative cycles. The Bellman Further algorithm can also be used to check if the graph contains a cycle with a negative plus, for example, the graph. Um, uh, who the hell is a faster algorithm for short space SPFI? Okay, thank you very much. But okay, now I see how this all works, but mainly it's not enough for solving tasks. Like, I mean, I like to know how to, let us consider how this algorithm works in the following graph, and the starting node is node 1. Okay, now I like to know how this algorithm works. Let's see. Like, I do all of them infinity, but aside one. Okay, let's in the distance of the search. Okay, how my steps looks like. I couldn't understand by what way it's going. Like, there's as you could see, was 3 of them. Also, there was 3 of them. Nope, nope. Yeah, 3 of them. I mean, I attack each of them. Okay. Initially, bam. Okay. So logically, it's going to be like this. It's 1 for 1. It's 0 for 2. It's 5. For 5 is 1. Like it's. I think that's already found. Like there's from 1 to 5. It's 1. Okay. Yeah. And that, yeah, like pairs. For 2 is 5 and others and others. In this case, the edge from node, and then like how they see, I start from 1 to all possible vertices, like it's 2, 4, and 5, but then how they continue. I mean, I choose the minimum one. Yep. In this case, the edge from node 1 reduced to the distance of nodes 2, 4, and 5, whose distance are now, yep, 5, 9, and 1. The next node to be processed is node 5, is distance 1. I choose the minimum, how would I say? This reduces the distance to node 4 from 9 to 3. Oh, like each time I took the minimum one. This is really deep. Like this is type of dynamic programming. Then from 1, nope. I mean, there's one. I found them. And because if we're going for its best one to take the minimum, and now, like, there was two. Oh, and then I sum it. Okay. Yeah, like 1 plus 2. Okay, then it means that for 4 it's 1 plus 2, like it's 3. Okay. Uh, After this, the next node is node 4, which reduces, like, I found again the minimum one. The minimum one is right now is 3. And 3, I like to show this. Like, if I want to go for 3, like, it's left one, and because of 3 it's 9. Yeah. Wait, no. Okay, now I feel the sense. No, I need the minimum one. It's the simple. Okay, like for example, how could I go to 3 is from 2. There's 9, there's, yeah, 5, 2, 3. This is really type of dynamic programming, like seriously, it's the same. Uh, okay, so this is going to be 7 if I don't miss. Okay, now like each time I need to choose minimum. It's not like simple like choose that and that. Okay. 1 is 0, 2 is 5, 3 is 7, yeah, 4 is 3, and 5 is 1. Incredible. Negative edges, implementation. Seriously? What the hell is that? Okay, now I see how them all works like. Okay. What about CPU algorithms? I mean, I know how to implement graph. Like for example, will we need it just to make adjacent matrix or adjacent list. Vector print register int s int adjacent size. The holy crap. Yeah, here it is. Difficulty. This is type of joke. I mean, shortest plus. So easy. I'm sure this. Okay, it was type of joke. So I will try my best for solving this. I'm serious. So mainly, okay, now I understood them, but not really clear because of I like to read again Siri, and then I like to move on for implementation. I really don't hurry up. It's already going for 28 minutes. Um, okay, so we are getting this. I would really like to know how to implement this. Like, I mean, this is really strange. You are given a directed or undirected weighted graph, only weighted. Graph is n vertices and m edge. The weights of all edges are non-negative. You are also given a starting vertex as the article discussing finding the length of the shortest passes um, from a starting vertex as to all other vertices and output the shortest path themselves. This problem is also called single source shortest path problem. Single source shortest path problem. Okay. Is an algorithm described by Dutch computer scientist Edgar W. Dijkstra in 1958. Let's create an array D with nothing, where for each vertex V, we store the current length of the shortest path from S to V. Wait again. Where for each vertex V, we store the current length of the shortest path from S to V in DV. I say you, this is dynamic programming. Like seriously, holy crap. Initially ds is equivalent to 0, and for all other vertices this length equals infinity. In the implementation, uh, in the implementation sufficiently large number which is guaranteed to be greater than any possible past length is chosen as infinity. dv is equal to this, and we can. In addition, we maintain a Boolean array. This is v or this is u. Okay, array u which stores for each vertex v whether it's marked. Like, is it in? Yeah, is it in array d or not? I'm sure this. It's marked. Initial all vertices are unmarked. Okay. So we go step by step, and okay, it's pretty good. The Dijkstra's algorithm runs for n iterations, on, if I don't miss. At each iteration, a vertex v is chosen as unmarked vertex, which has the least value dv. Okay. Evidently, in the first iteration, the starting vertex s will be selected. The selected vertex v is marked. Next, from vertex v, relaxations are performed. All edges of the form v2 are considered, and for each vertex, the algorithm tries to improve the value d2. If the length of the current edge equals len, the code for elections is. I mean, how if I don't miss its own length and something new? And the main problem is that how do we get this d2? I just want to know this. Okay, let's read this again. Enters, and each iteration a vertex v is chosen as unmarked vertex which has the least value dv. Evidently, in the first iteration the starting vertex s will be selected. The selected vertex v is marked. Next, from vertex v, relaxations are performed. All edges of the form v2 are considered, and for each vertex, the algorithm tries to improve the value d2. If the length of the current edge equals len, then code for relaxation. The code for relaxation is this. How do we d2? I have the question. Oh crap! We're also restoring. Like, it's really. Oh, wait a minute. Each of d2 is infinity. Okay. After all such edges are considered, the current iterations ends. Finally, after n iteration, all vertices will be marked. And the algorithm terminates. We claim that the found value dv are lengths or shortest paths from S to all vertices v. Wait a minute. Claims that the found values dv are lengths, so all shortest paths from S to all vertices v. Note that if some vertices are unreachable from starting, okay, like if you don't have any edge, from starting vertex S, the value dv, for them v will remain infinity. Obviously, the last few iterations of the algorithm will choose these vertices, but no useful work will be done for them. Therefore, the algorithm can be stopped as soon as the selected vertex has infinity distance to it. Okay. Holy crap. We have proof and we have restore short passes. This is on at the square. Holy crap. We have something. Okay, we have also surpassed. Okay, we have this and we have this. Usually one needs to know not only the length of short paths but also the short paths themselves. We would see how to maintain sufficient information to restore the short paths S to any vertex. We will maintain an array uh, predecessors P in which for each vertex V is not equal to S, PV is the penultimate vertex in the shortest path from S to V. Here we use the fact that if we take the shortest path to some vertex V and remove V from this path, we'll get a path ending in vertex PV, and this path will be the shortest for the vertex PV. This array of Okay, so there of predecessors can be used to restore the shortest path to any vertex. Starting with we repeatedly take the predecessor of the current vertex until we reach the starting vector S to get the required shortest path with vertices listed in reverse order. So the shortest path P to vertex V is equal to P equal to the S. Then mean hell no. Like, are you joking, man? Building this array of predecessors is very simple. For each successful relaxation, when for some selected vertex V, there is an improvement in the distance to some vertex 2, we update the predecessor vertex to this vertex V. Dijkstra's algorithm prefers n iterations. On each iteration, it selects as unmarked vertex v with the lowest value dv, marks it and check all h's no it's v to 2, attempting to improve the value d2. The running time of the algorithm consists of this. Answers for vertex with the smallest value dv among O n unmarked vertex. M relaxation attempts. Wait. For the simple implementation of these operations on each iteration, vertex search requires O n operations, and each relaxation can be performed in O1. Okay. So, holy crap. This complexity is optimal for the dense graph. However, in sparse graphs, when m is much smaller than the maximum number of edges n squared, the problem can be solved O n log n plus m complexity. The algorithm and implementation can be found in the okay. Here's the contest infinity vector pair int then adjacent void Dijkstra int s vector d vector p. What is vector d? Okay, Dijkstra and vector p was about unmarked. Hold on, man. Okay, inside the assign. What's assign in C++? Few, if I don't miss. D is equal to the 0 for int 0 e is less than n, int v is equal to minus 1 for int j 0, j is less than n, j plus plus if oj, okay, it's not used, v equal to the minus 1, also dg is less than dv. Okay, I have a big question, like, why do I need to Uh, okay. If the v goes to the infinity break, v true for outer edge adjacent v into edge first into line edge second. D2 equals the dv plus line p2. Uh, I want to see the whole code. Like, uh, is it enough just to store uh adjacent matrix? Show me full version of code. Okay, so let's get started. Okay, I have nothing. Let me ask me. Okay, this adjacent list. Okay, so this is um full of code. Now let me copy this. Let's go to the VS Code. It's next to non-cell. The starting source code vector store minimum distance from S. Vector to the store producers used to research the path. Find the unvisited vertex with the smallest distance. Mainly it does it by adjusting list. Like, hello man, what the hell is that? I wasn't supposed to learn this. Okay, so I like just to learn this code for full. First, I want to know what's a sign in C++. Okay. In C++, assign typically are two distinct classes. The assignment operator used to and the assign member function used with standard template library still contains like vectors and strings. The assign method online operator, which usually replaces one container with another or the same type, is more flexible. Clears and replaces fills the vector with 5 instances of the number 10. Like, wait a minute. Fill with value v fill a vector with 5 instances of the number 10. Key differences, wait a minute. So, oh, just double circles. Mhm, mhm, mhm. A sine function clears the context of a vector and then fills it with data. There are two ways specified, like here's the context of a vector and then fills it with data. Okay, I see you. Um, okay, right there, I get size of my graph. I'm sorry. Then we have the assign. Okay, I fill it with n numbers by infinity. This is Dijkstra array, and this is I don't know, vector build. Like how I use this element or node. ds equal to the 0. I haven't found it. For int e0 e is less than n e plus plus int v equals to -1. Find the unvisited vertex with the smallest distance. For int j, wait, find the unvisited vertex with the smallest distance. If it's not used and I haven't found the vertex and dj is less than dv. Like hell no, man. Okay, so this is unreachable. Okay, from vertex v I try to go for each of them and then I modify v for going for next nodes. Okay, pretty good, but why do I need s right there? I just feel it. Okay, um like, okay, I've already used this and mainly I want to um fully understood this part of code. Mainly this pretty understandable, but I couldn't understand why v equal to -1 for the honest. Like, it's impossible to find because d -1, what the hell is going on? And also, what's p array? I haven't waited. Yeah, how the CPRI is about this predecessors, if I don't miss. Then for auto h in adjacent v, okay, int 2 is going to be edge first. Like, I mean, I get like this type of adjacent right there. This is the node. Okay, and this one is connected and wait a minute. How adjacent list looks like? Okay, so the value and its weight, the value and its weight, the value, I mean node weight and others. Okay. Oh yeah. Okay, let's see that. Then we do into edge first and planning up. Okay, and here's a relaxation step. If dv plus len is less than d2, I do d2 equal to dv plus len. P2 equal to the V. Like, I mean, what the hell is P? Right there. Be honest, I haven't cared about restore pass implementation. Okay, let's try to now understand what's PRI. Well, let's ask this by Gemini. I think so. Wait a minute. Yeah, let's go. Is it past like there? Just algorithm that repeat right stands for predecessor or parent. Okay. Now I just want to know what's predecessor. I can understand well it is. Its purpose, the PRI stores the previous node for every vertex. Specifically, PV stores the ID of the node that immediately processed V on the shortest path from the source. How to update it? Wait a minute, no, I cannot send again. The PRI stores the previous node for every vertex. Specifically, PV stores the ID of the node that immediately precedes V on the shortest path from the source. Okay, so this is type of parent array um, that's going to be used in this. Nope. Result P array. You would know the shortest distance from city A to city D is 15 miles, but you didn't know which cities you drove through to get there. By following the P array backward, you can reconstruct full paths. How to reconstruct the path? Wait a minute. You wouldn't know which cities you drove through. Oh, okay. So, like, what nodes I have used for getting to this node. To find the path from the source to the target, you start at the target and work backward using the p-values until you hit the source, which is marked with -1. Example logic: suppose you want the path to node 5. Check p5 is 3, check p3 is 0, check p0 is -1, stop. You have reached the start. So the path is 0, 3, 5. Holy crap, okay. Okay. The distance weights. How far is it? P predecessor node IDs. How do I get there? Okay. Mainly it's okay. I understood it. And okay, mainly right there P2, make it V. Okay, right now I understood all of this and I like to repeat this again. Oh crap, it's really hard to understand. It's already gone for 54 minutes of studying Dijkstra algorithm. I won't do that again at my life. Okay, the first part we have understood this. Restore path int s int t vector int constant p vector path. So I start from t. What the hell? I need some CP right now. What the hell is it? Function to reconstruct the path from the source to the target. Okay. So like I couldn't understand anything. Let's ask this from AI. And yeah. This helper function is the final step of the algorithm. It takes the breadcrumbs RIP and curves it into a repeatable list of nodes for the start to the finish. Here is the breakdown of which part of this logic is doing. Since each node only knows its parent, we have to start at the target T and jump backward. If the parent of 3 is 2 and the parent of 2 is 0, the loop collects 3 to 0. The loop stops when it hits -1, which is value we assign to the source node's parent. Reversing, oh, okay, like from parent to its child, to its children. If passes, okay, what the hell? The no pass safety check. If pass size okay. Because we collect the nodes by walking backwards from the destinations, the vector is currently target to the source. But we need source to the target. The no pass safety check. If pass size equal to the 1 and pass equal to the 0, then return nothing. Oh, no vector, yeah? This is a crucial edge cases. If the target T was never reached by Dijkstra, because it's disconnected from the source, its distance remained infinity and its parent remained -1. In this case, the loop would run exactly once for v equal to the 2, then immediately see pt equal to the -1 and stop. I couldn't understand anything again. Pass 0 to 3. Like, do I just find the pass? I return pass, no pass found. Okay, so it's for each of them. Okay, pass pushback we and mainly. Oh, this is predecessor's array and its parents. Okay, okay, I understood this. And okay, finally we go to the part of this. Mainly, okay, I see. Like, I make vector p and I have predecessor's array. It saves its parents and mainly for v and until v is not equal to the -1, make v equal to the pv. I go by its parents. Like, this is the same was at the DCO, disjoint set union data structure. Pass pushback v and then reverse it and then return it. Okay, and now the main problem is that I don't know how to work this adjacent list. Or every time I'm starting this adjacent matrix, it was easy to input, and now what about adjacent list? How to input? Oh, like it's easy, like it's type of map. No, I do vector, now I do pair right there, and it continue as an tuple, if I don't miss. But at the tuple is going to be, holy crap, some pairs. How to input adjacent list? Let me take this. Go to the int main. And now it's mh. Reset the adjacent. Wait. N is vector int and int, and okay. Okay, now I have this script and show me how I would like to go from 1 to n. Holy crap, what the hell is that? Is this all int main, like right there? Yeah. Yeah, so I just think we want to go from node 1 to the start node 0. 0 indexed, yeah. I have only see this. Check if target is reachable. Start node D and P. I haven't made D and P. No, I don't care about fast. Holy crap. It's really freaking hard. Okay, so I took a rest at my mind, and mainly, where's DNP Rise? Are you joking me, man? Oh yeah, here we are. It's about okay, so check if we want to start from one. Like, I mean, here we go to the target node. The target node is enough. Mainly, if I don't care about pass array, could I delete this? I don't need this at my task. Oh, yes, can delete this. Right, so my source code is going to look like this. Yeah, something like this. If we delete this, then we delete this. Yo, oh, okay, I missed. There is shortest distance. Wait. Totally, if I also do like this, totally eats 52. Holy crap. I didn't expect this. Like, we also could do like this. There's going to be 0. Wait. Why the hell I need target node? I just could do this. Okay, so something typical to this. No, I will try to implement this. Oh, I like to study this code. Like, I mean, I was going to learn this as a poem. Hell, man, I wasn't supposed to learn this. I'm not even people in God of Forces. Like crap. Okay, so I think so. We are going to have some 5 minute break, and we are going to see us. So I come back right there. So let's get started again. Starting Dijkstra algorithm. Okay, so as we know the task, and we made script for 48, uh, 48 sets of code, and I will try to just learn it. I don't have anything else to do. Um, so I'm going to last time to treat the script for navigating future problems. Yo, what the hell is that? Now, just treat the script. Optimization script. Yo. No, yep. No, it's the same. Okay, so I'm already going to be delete this and delete this for a while, but no, it's going to be needful to me. Okay, and let's open this. Okay, so we just make bases, and bases are infinity. Let me just do this one here. 8. Oh crap. Then let's, for example, do this long, just for fun. No, we could also do this int. Peer int adjacent list. We have a target, and we have a vector int Dijkstra, like Dijkstra's own array, like the maximum, and we have the assign in infinity. What is it? The assign in infinity. Yeah, we just fill it in. We have vector bool, and like we haven't used them all, like it's falses, and d is equal to 0. As you know, at the simulation of the computer programs handbook, it was given as a 0 for the start value. For int, okay, and we just make just simple loop. And wait a minute, what this loop is about, let me remember this. Why we, okay, we just look at our graph, and we have int v equals to the -1, and int j is equal to 0, and j is less than n, and we again look at our graph, and if we haven't used this element and v equals to the -1, oh okay, if our finded element critically less than v, or v equals to -1, like the start value, we make v equal to the j. Why? I'm not. Oh, dv, what's dv? Like, I haven't filled it. And also, what is, like, for every element, like type of vertex? Oh yeah, I do it for every element as a brute force. Oh crap. And then you have integer j. That's also working. Okay. Make v equal to the j, like for finding the next elements, if I don't miss. Then if dv equals to the infinity bracket, well, we just could do it like this. I'm not in favor of splitting this. Okay, something this type. No, it's 41. Oh, I'm glad. Okay, and logically, then we do v equal to the true. Yeah, we look at the all array, like, oh crap. Um, the main problem is that I couldn't understand this loop for full. For each element, I do this. Int v equal to -1. Okay, like each time it's real understandable, it's not understandable. I just couldn't understand why there's while loop. How would I see it's just for looking for the all of elements. Yeah, if I don't miss. If I couldn't find this normally, like it's still okay. So each time I change its value as j, and if its value is still infinity, then get off here. Um, yep, and then I make it true. Like if it hasn't worked, then I do this loop. This is already om, and int 2, like where I need to go, and int its length, like its weight, dv plus len is less than d2 is going to be equal to d2 is equal to dv plus len. Holy crap. Then int n, okay. Mainly this array is really scary, like I've already made this right there, and because I don't care about. Oh, okay, so right there, I make vector pair int and this. I don't know why. Okay, this is n. Okay, mainly. Wait. I could understand this. Like n, it's less n. Okay, it's spread ensemble then vector. Yeah, this is type of vector, and yeah, it's like type of pairs, the node and its connected nodes, and there could be tons of them, like lots of them. Like I mean, it's of nodes and itself weights, and because if I put this, okay, then vertex weight, vertex weight. Yeah, I make a pair and I just put it back it. Yeah, like for example, it's if this vertex is the same, it's going to be like this type. This u vertex is connected to this vertex, and it's also connected to this vertex, and this goes because if I push back, because if I use vector, if I don't miss vector int, then I fill it, and then I take the shield. What about it's just simple one. Nope, it's not simple one. It's vector and the vector. Yo, it's always a vector. Where's the Okay, I couldn't understand. Is this type of another array? I couldn't understand. Like, whoa, what is this? I don't need this. Okay, let's write its code. Let me open code blocks right there. Okay, I'm going to save this code. Compare. Yeah. This stream is going for already 1 hour and 20 minutes. Open an existing project means CBP. What the hell is that? Okay. Firstly, we need to make with Dijkstra. With Dijkstra. Int s and vector int is going to be d. Let's put it like this. Then let's make some conferences. I mean, const int infinity is going to be cool fun for 1 year 9. Then let's make int is going to be size of what? Like here we are going to make vector. Where's vector? Where's pair? Where's int? I blocked this, and adjacent. Okay, and one of this. Int adjacent size. We make int is equal to 0. It's going to be like as an bool, and there's I'm going to put like O and this false size of n. No. And at least we should found or the what if dj is less than dv, make mu equal to the j. If I couldn't find this, break. Like what the hell I did? Let me just make it simple. And then there was something I don't remember, like what's it about? Yeah, make uv true. Then for auto adjacent. Okay. Mainly I don't care, for example it's going to be in, okay, adjacent v. How can I name this? Like x. Then let me make int q. It's if I remember, int weight. Yeah. Okay. Int q is going to be x first. X second. I don't remember what was there. If d2 is if d2 was dv, no, first it was len. If dv plus len is critical less than d2, then make d2 equal to the dv plus len. dv I don't return anything. Okay, so there's good. I just want to check, is there any completion errors? Are there any completion errors? Nope. Okay, I'm glad. Now, for example, holy crap. I took input like this, int n, and sin n, adjacent list assign, and then I do this, and this vector where pairs is int for int and 0 is less than n e plus plus int v and then wait. Oh, I know I need to push back. Push back this up. O and wait. And then I need to make some vector int d extra 0 and d, and then if wait, yep, it's void, but if d0 is equal to the infinity, then cout -1 and return at the else position, just cout d0. I think so I missed because I need to print the n-1. It's good. Is there, are there any completion errors? Yeah. Now also make the assign in and false, no, infinity. Yep, I really don't know what's the problem right here. I can Google this. Okay, I'm pretty dumb. It needs to be right there. Yep. Wait. What's the problem? I mean, I just push back. OV. Now I'm really like pretty done. Like I make pair and I just push back it. Like for example, make pair. Pair is going to wait. Like what if I just do type of this make pair O and W. Okay, Control S and then run my code. What's the problem? I couldn't send really like okay, I was doing the same, but okay, the same like I can just copy this and then I go right there. I couldn't name this error. Like, what type of error is this? Let me put my code. Let me make like I find to the VS code. It was the same, right? Oh crap! I'm pretty dumb. What type of error is this? Yeah, I'm pretty dumb because like I connect U with V. That is the critical problem. U minus 1, then push back V minus 1 and W, I guess, and zero index set. Minus 1. Is it zero index set? Nope, it's not. So let me Control S, then say my code, then okay, and mainly the main problem is that I was remembering that I need to use parents. But the main problem is that why my code doesn't work well. Like it doesn't even give me the value or something else. Let me just find this problem. Holy crap, yep. Just M. Holy crap. Mm-hmm. Yeah, let me just copy this. I don't hope that's going to work. Um, but let's also do it this. Okay. 5. At least I found. Holy crap. At least we found the sum. Meal is going for 1 hour and 7 minutes. My eyes are done. My brain just doesn't want to stop. The main thing, I'm just blind man that couldn't understand that they was using parents. Holy crap. Now I need to make vector for parents and I'll try to solve this task. That's all. um, the n minus 1 0 d. Yeah, that's good. The main problem was there and there, and then I don't know. No, and then there. Um, wait a minute. Okay. Yeah, it is the same as okay. So the next thing we need to make parent arrive, and then we need to make a restore pass function. So how do I know? I copy this and name it P, and then I save it. There, I just need to make P something. Make something. Like I don't know, just at least, and there's going to be vector. What do I mean vector function? Okay, like this. Restore pass, and then I think so. Return pass. There's going to meet vector int pass. There's going to be, and like I need to give vector int and p right. Then for example code goes here. Okay, so let me also do this. I don't know what about like I think so PV equals to something like I'm really OD2. Let's enter for CPU algorithms. And we go to the instructors. Restore. Oh crap. P2V. Oh yeah. Like the way I go, its parent is there. Like okay. Oh crap. Like 2 from V I go to the 2 and holy crap I'm pretty dumb at this station And then here we go. I don't know really. It's going to be type of mm, some there then reverse pass dot begin, then pass dot end, then right there I like just to return. Oh, there's already. So now my code goes here, and also it goes here because I remember there was some type of if. Let me remember this if. Mainly the constructor was like this. Return. Now if I copy this, I think so. They're holy crap. Int v something. I don't know. -1. No, it's not enough. Like I don't remember. I was giving like PV is going to be equal to T type of this. Yeah, V was equal to T and V until sent equal to the target. No, like it's not enough. Is it? Oh, crap. So for int V is going to be equal to T and V is less than this. Okay, let me copy this. I'm not a fan of writing code again itself. I missed so much, really so much. Is it S and target? I don't know. Well, V equals to target and it's not. Yeah, I go down and down. As it was 0 and n-1. Let me just copy this. Let me make this construction. Then vector int pass is going to be type of what? Like I mean, I start from 0 and going for -1. That's all. And okay, wait a minute. Now I need to make pri vector int p. Holy crap, the output is just blowing. Okay, let me see the CPU algorithms again. Like, um, yep, yep. Like it's the same, like the same of the same. Mm-hmm. But it's possible that I missed this T. I couldn't understand what is this. What is it? Adjacent. So let me just research for this. Mm, so I'm going to say create my code. So this is a there's a problem like okay, I'm sorry. So let's get started right there. So however, I don't know how we get PQ. This is prior to no, 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 nope, 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 man. Really? No, please, no, man. Like I haven't. I'm not ready for this. Be honest. I have seen these types saying like right there on sparse graphs. Yeah, it was the same one. No. Yeah, it is prior to Q, man. I don't know why doing it prior to Q, but let me just take it. Skip outside peers. So let me run this code. Okay. It's the same. Nothing changed, like man. And I'm really seriously right now, like nothing changed. Um, okay, I just forgot to add +1. Bro, are you joking? Yeah, but I think it's the same. This is my previous code. I hope. Bro, are you joking? From 1 to the 10. Hmm. I just go right there. I think it's this, if I don't miss. What's the answer? 7 through 10. 8, 7, 3, 10. Yep, okay, I see this. I don't know why. It's not my problem. Like, I don't think so. It's even going to help me. Like it was the same. I just forgot to add +1. Include. Mm, so it shows this as this. And it's type of same thing. Like, is it going to work? Holy crap! Finally, just finally, we made this. We added this and this. I don't know what's practical, but I'm just glad for doing this task. It's okay. Let's. Oh crap. Okay, I sorted by greater. Okay. So how would I see just made it totally so like type of okay, so he made restore pass function right there, and also he checked it right there. Mm, okay, yeah, so it's undirected. Holy crap, it could be my mistake. But okay. Um, okay, thank you for watching this video. Today it was really hard, so I tried my best for explaining you just so I can explain to myself even. So, thank you. See you later.